My name is Mohammad. I am a PhD student from Binghamton University Mechanical Engineering Department. I and my friends Mohammad Alzgool and Professor Towfighian are going to present enhancing open loop control of MEMS using linear electrostatic levitation actuators. Decreasing the overshoot and settling time is important for MEMS actuators used in optical micrometers. Open loop control methods are becoming more popular in MEMS because of their simplicity. As shown in this figure, actuating the dynamic system with only one pulse, a large overshoot and settling time will appear, while using command shaping lowers the settling time and overshoot. However, the MEMS parallel plate mechanism is highly nonlinear and limits the range of motion because of pulling instability. The nonlinearity demands more complicated command shaping methods such as zero velocity and derivative. In this presentation, we have added the electrostatic levitation to the parallel plate mechanism to address the mentioned limitations. Electrostatic levitation is the actuation using the fringe field effect. Adding two side electrodes to the parallel plate mechanism enables the movable electrode to travel toward the opposite direction of its substrate. In this way, the initial gap between the parallel plates is increased, and as a result, a wider operation range is provided. In terms of the relation between the input driving voltage and the resulting force, the capacitive force between the parallel plates is highly nonlinear when the gap between the parallel plates is small, while the dependence of the capacitive force on the gap between the parallel plates is negligible as the gap is sufficiently large. They also provide tunability because of the higher degrees of freedom in shaping the electrostatic field. In the next two slides, the results and discussion will be presented. This figure shows the experimental results of the static displacement versus the square of the driving voltage in the presence of different DC levitating voltages. For the zero levitating voltage, which is the same as the conventional parallel plates, the range of motion is 0.36 micron, while applying 100 volts of levitating voltage provides 2 microns of operation range, and adding 120 volts of levitating voltage provides 2.48 microns, which is approximately 7 times larger than the conventional parallel plate range of motion. Also, this figure shows that as the levitating voltage goes higher, the region of linear input to output gets wider, which is useful for open loop control. This figure shows the experimental results of applying a linear double-step command shaping on the levitation MEMS actuator. The left axis shows the input and the right axis shows the output displacement. The displacement of half a micron and 1 micron has been selected for this experiment. At different levitating voltages, the mentioned displacements are achieved, while this has not been possible with the conventional parallel plate mechanism. It also shows that the linear open loop method works well for the parallel plate capacitive actuation when the electrostatic levitation is implemented. Using the levitation electrostatic actuators, we improved the motion range of the conventional gap closing mechanism 7 times. In terms of linearity, levitating the movable electrode keeps a large distance between the driving and movable electrodes. Operation at this region provides a linear input to output relation. Linearity enables the application of linear command shaping methods such as double step drive. And thank you for listening to this presentation, and please contact us through our website and email.